Welcome back, everybody. So we're going to be starting our next unit, which is going to be an extension of Unit 7, where we looked at trigonometric functions. Now we're going to be looking at a number of trigonometric identities. So this is going to be kind of getting into the algebra of trigonometry. And so an identity, in the simplest sense, is just an equality of equivalent statements. So two statements that are equal to each other. But most importantly, they're equal to each other for all values that are possible. So all values within the domain of those specific expressions. So up at the top in the box here, we've got some known trigonometric identities that we've worked with in Unit 7. So in particular, the reciprocal identities, cosecant, secant, and cotangent, which all related to the sine and cosine functions. So in this case, cosecant is the reciprocal of sine, secant is the reciprocal of cosine, and cotangent is the reciprocal of the tangent function. And for tangent, it's going to be very useful to remind ourselves that tangent is the ratio of sine to cosine. So that we derived from the unit circle, where we saw that tangent theta was equal to y over x, and y is the sine value, x is the cosine value. And then finally, the last thing to check is kind of the symmetries, the odd-even symmetries. And so these can be verified by looking at the graphs of the sine, cosine, and tangent functions. And so what we'll note is if we put in opposite input values, so if I put in negative theta to either function, I will get the opposite of the positive value of theta if we're odd, or I will just get equivalently the original expression, as is the case with cosine. So cosine is an even function, sine is an odd function, and tangent is an odd function. And so again, we can kind of think of this graphically if we wanted to. So if we think of the sine function, which is that wave function starting at the origin, it has that odd symmetry about the origin, meaning for any value I choose, let's say a negative angle measure, the positive opposite of that will have opposite sign. So this will be positive and this will be negative. So we can see that sine of negative theta is going to be equal to, let's say, negative rad 2 over 2. But that's going to be, so this is negative rad 2 over 2, but that's the same as negative sine of theta, because this is positive rad 2 over 2. So again, we can verify those symmetries really easily, and having this is going to be really nice, because if we're given a negative theta expression, we can rewrite it in terms of positive theta. So again, just another tool that we'll be able to use to kind of manipulate expressions. So going back to our notes here, we're going to look at kind of the starting identity, which is the Pythagorean identity. So given our triangle here on the left, we can label our side lengths with the lowercase letters corresponding to the angles opposite, or angles of the vertex where the side length opens up at. So we'll note that a squared plus b squared is equal to c squared by the Pythagorean theorem. So again, we'll note that we've got a right angle at angle C. But now we're going to manipulate this to introduce trigonometric expressions. So I'm going to divide both sides of my equation by c squared. And we'll note that c is greater than 0 since it's on this triangle. So we don't have to worry about division by 0. And so that's going to be a over c squared plus b over c squared is equal to, well, c over c squared, or just 1. But what we'll notice here is if we call, let's say, this angle theta, sine of theta is b over c, opposite over hypotenuse, and cosine of theta is a over c. So what that means is that we can then substitute into our expression here those sine and cosine expressions. So what we'll end up with is a over c is cosine squared of theta. And we can write that as cosine quantity squared if we wanted to, plus sine of theta squared is equal to 1, and that's our Pythagorean identity. And note, cosine squared theta plus sine squared theta is equal to 1 for all values of theta. So it doesn't matter if it's 2 degrees, 100 degrees, pi degrees, 2 pi over 3 radians, any angle measure that we choose, this will always be true. And sine and cosine have infinite domains. So this is true for all values of theta, which is really all real numbers. So this is a really, really nice identity. And so from this identity, we're going to derive a couple of additional ones. So a couple that are going to be additionally useful. So the first is going to be kind of the isolation identities. So in other words, I could take my expression and subtract sine squared theta on both sides. And if I do that, we'll note that cosine squared theta is equal to 1 minus sine squared theta. So this is just manipulating properties of equations. I can subtract or add the same quantity on both sides. So in this case, I'm subtracting the sine squared on both sides. But I could also have subtracted the cosine squared. So now we could solve for sine squared as well. And we'll get 1 minus cosine squared theta. And these are going to be really useful. And maybe we'll start numbering these, because this allows us to rewrite sine and cosine in terms of each other. And this is a really, really nice property that we're going to use quite often. What I'll also note here is that this is a difference of squares in each case. So that means both of these expressions, 1 minus sine squared, 1 minus cosine squared, those are both factorable expressions. So just as a note, 1 minus cosine squared, for example, is equal to 1 minus cosine theta quantity times 1 plus cosine theta. And that's going to be useful because we're going to be using lots of factoring techniques as well. So let's look at 2 additional properties or variations on the Pythagorean identity. So we'll start by kind of rewriting our identity here. And I'm going to put the sine squared in front. And so let's suppose that I divided everything by sine squared. So if I do that, what we'll notice is that sine squared over sine squared is going to be 1. Cosine squared over sine squared is going to be the cotangent function squared, because cotangent is the reciprocal of tangent. And then 1 over sine squared, well, that's going to be cosecant squared. So now I have an identity connecting cotangent and cosecant. And what we'll notice is we could do the same thing with cosine squared. So we'll divide everything by cosine squared. And what we'll end up with in this case is going to be tangent squared, because I have sine squared over cosine squared, plus 1, and then 1 over cosine squared is secant squared. So from this one Pythagorean identity, we actually have 5 variations. And again, these variations are going to be incredibly useful once we get into the more complicated types of proofs where we need to switch between forms, as well as solving equations. So these are the 5 main ones that we're going to start with, and these are going to be ones that you're really going to want to know. Note, very easy to derive. You can always derive it from the Pythagorean theorem, but these are ones that you'll typically commit to memory. So moving forward then, we're going to have to kind of discuss, well, how do we know if 2 identities are equal to each other? Because we're not always going to have a nice Pythagorean theorem that we can just kind of use, which we've already proved in previous courses and we already know is going to be true. So we're going to kind of discuss proving techniques for trig identities where we're going to use kind of the algebra of what we know about these expressions to show that they are equivalent. So the first example down here is tangent x sine x plus cosine x is equal to secant x. And so what we'll note first is, let me move to a smaller font. We don't know if this is true, right? So it's asking us to prove that this is true, so that kind of leads us to think, okay, maybe this is true. But if I wanted to check for every value of x, right, there's an infinite number of x's. So that's going to be very cumbersome to actually show that it's true for every single value of x just by plugging in and checking. So note that's not going to be the route that we want to choose. So what we're going to do is we're going to choose one side of this equation. So I'm going to call that the left-hand side or the right-hand side. So note this would be the left-hand side. This is going to be the right-hand side. So I'm going to pick one of those, and then I'm going to start manipulating it algebraically to show that it's equal to the other side. So we're going to kind of want to know, well, which side should I choose? So it's not always going to be obvious, but in general, you want the side that's more complicated, that's going to offer more options for you to manipulate. So for this proof, we're going to choose the left-hand side. So I'm going to rewrite that. So for our proof here, we'll rewrite tangent x sine x plus cosine x. So this is my starting point for my proof. And now we're going to want to change this expression in a way that allows us to show that it's equivalent to secant. So for this, if I'm looking, not really much I can do in the current form that it's in, right? There's no multiple sines or multiple cosines that we can factor. So the key here is probably going to be tangent, because I know that tangent can be written as sine x over cosine x. So this is really sine x over cosine x times, and then I'm just going to rewrite sine x as maybe sine x over 1. And then we still have plus cosine x. All right, so now we can maybe combine the signs. So we've got sine squared x over cosine x plus cosine x. Now I want it to be secant, which is a single expression. So I'm probably going to want to combine these two terms. So in order to do that, we're going to need to find a common denominator, which in this case is cosine. So I'm going to multiply and divide by cosine. So what we end up with is sine squared x plus cosine squared x all over cosine x. So our tangent x sine x cosine x expression is equivalent to this expression, just by manipulating some terms and finding a common denominator. But where do I go now? Okay, take a moment, see if you can see it or not. So we've got sine squared plus cosine squared and cosine x. So the cosine x, nothing I can really do with that. But sine squared plus cosine squared, well, we can do something with that, because we know that that's equivalent to 1. So by the Pythagorean identity, we know that this is equal to 1 over cosine x. But 1 over cosine x is equal to secant x. And that is the end of our proof. So now your proof is going to just kind of have a little pathway, a little sequence of movements. And note, at no point in my proof did I refer to the right-hand side. So it was as if the right-hand side didn't even exist, and I'm just discovering what it's equivalent to. And so that's going to be the key for these proofs is once we choose a side, we ignore the other one. It's as if the other one doesn't exist, but we know in the background we're trying to make it fit that expression. All right, so we're going to take a quick break here, and we'll do a part 2 hopping into the identities here. But what I would recommend is before doing that, maybe try these first 6 on your own, noting that not all of them are true. So some of these may be false, so don't just assume that it's going to be true. and use that proof technique that I just talked about a moment ago. So until then, I'll see you later.